This is going to be Federation of Kubernetes Clusters, aka Ubernetes. Give it up for Quinton Hoyle.
Thank you very much. The graveyard shift of the afternoon, always a tough one. I'm very well aware of the fact that I'm the only thing between you and beer, and I take this responsibility very, very seriously. Yeah, we hopefully will have some discussion time left at the end for questions. And with no further ado, I'm Quinton. A little bit of history on me. I'll stick to the pre-Jurassic period because there's quite a lot of it. But 2005, I started the EC2 project at Amazon. Did a fair amount of the development and ran that for a few years. Then did a startup, essentially built the same thing again, a company called Nimbula. Again, an infrastructure and a service, as a service in a box, essentially. I then joined Google a few years back, ran the ad serving systems there for quite a while, which, as some of you will probably be aware, you see lots of ads. They're quite big systems, and one of the bigger ones at Google. And more recently, in the last year or so, I joined the cloud team. I think they wanted some people with less hair and more gray facial hair, something like that. So that's what I've been doing for the last year on the core Kubernetes team. That's me. Those are my handles and things on the screen. So, you know, a lot of this whole Kubernetes hype is all about these big data centers, and you've probably seen pictures like this before from Google. We got these enormous data centers with lots and lots of anonymous-looking machines in them, and your beloved application is somewhere in that huge data center. And one of the messages that gets kind of repeated over and over and over again is like, don't care about the individual machines, don't worry where your application is running, we'll sort it all out for you, the software does all that for you. All you do is you tell us what you want to happen, and it all gets, you know, splurged across these enormous data centers. One thing that we sometimes forget about is that we also have quite a lot of these data centers. I remember back in 2005 when I joined Amazon, there were still people walking around Amazon talking about the data center. And we kind of occasionally had to remind them we have 3 of them now. You know, we've got 3 data centers. You've got to tell us which data center you're talking about. And that was kind of quite funny. I had a quick look at AWS's website the other day, and I see they have, what is it, 30-ish availability zones now, 27 or something like that. So the times have changed quite a lot. As you can imagine, talking about the data center at Google when you see what's on the screen in front of you doesn't make a lot of sense either. And having run some of the big systems at Google before, you very, very quickly lose track. You know, you're running a single, you know, logical application across maybe 30 data centers. You can't remember the names of these things. You can't remember where they all are. You just want to say declaratively, you know, make sure that there's enough capacity on all 3 continents in the world all the time, and you figure out which data centers are being refurbished, which ones are disconnected from the internet, which ones are having a flood today. On any given day or week, you know, multiple of these things will disappear from under you. So it becomes very much the same problem that Kubernetes has been solving with respect to individual servers. You know, that problem very quickly becomes the same sort of thing at a data center level. So this is a picture you've probably seen if you've been to any previous Kubernetes stories before. We treat the things on the left of that slide a little differently than we treat the things on the right of that slide. It's not a very intuitively appealing thing. The humanitarian side of us doesn't like it very much, but from an operational point of view, in managing applications, it makes a lot of sense. It allows us to automate a lot of things. And having these sort of relatively anonymous things on the right-hand side is a lot easier to deal with and to automate than having these beloved things with individual names on the left-hand side. So the same applies to data centers. I'm not saying you can't give your data centers names. All I'm saying is that, you know, a lot of the automation and anonymity that we have been proposing and encouraging people to adopt with respect to machines applies equally to data centers. So if you're not familiar with this picture and you can't tell me what all the labels are with your eyes closed, you're probably sitting in the wrong room. So this is not here to teach you about, you know, what Kubernetes looks like roughly. But just to remind you, you know, roughly what you've got is users on the left-hand side interacting with a control plane, and there's a whole bunch of stuff in that orangey red box that I've left out intentionally. And on the other side of the control plane, there's a bunch of typically physical machines or virtual machines on which we sort of move these containers around, connect them together, attach them to storage, etc. So none of that is new, but worth noting is that thing in itself is a cluster. We call it a Kubernetes cluster. There are various things that are kind of constrained to a cluster. So the way you discover services, some of the DNS services that run in there, the amount of capacity available is constrained by a given cluster. A cluster typically runs, not necessarily, but almost always runs inside a single data center or a single availability zone. And that has various sort of implied positive and negative attributes. So what happens if we kind of explode this a little bit and we say all we really care about, and then you'll notice the question mark at the end there, this is oversimplifying things a lot, is we want to interact with an API and we want, you know, our applications on the right-hand side in the green there. We want our applications just to work the way we want them. And we don't really care that they're in a cluster, and we don't really necessarily care that there are multiple of these clusters or multiple data centers scattered all over the world. So enter what we have started calling cluster federation, which somewhat not by design, but just by accident has become known as Ubernetes, thanks to Justin, who I think is probably in the room here somewhere. I think coined the term. The basic idea is to take multiple Kubernetes clusters and tie them together in a sensible way that we can solve some of the problems that are more difficult to solve when we treat clusters individually. The architectural model you can see is, you know, roughly the same by intention by me, drawing the same picture, but a couple of notable things to bear in mind there. Can everybody hear? Yeah. So firstly, you've got multiple availability zones on the right-hand side, so you can solve various problems that require that, for example, high availability. You also have multiple cloud providers on the right-hand side, so that helps you solve multiple problems, for example, moving things from on-premise data centers to the cloud, moving things from one cloud provider to another, and we'll talk about those a little bit more. And we collectively call this group of Kubernetes clusters a federation for fairly obvious reasons. So the word Ubernetes and the word Kubernetes Cluster Federation are roughly analogous in the context of this discussion. So this all sounds very exciting, and we're building big astronautical architecture models, and this is all makes for very good academic papers, and people get very excited about it. But why is this at all interesting to us is a perfectly valid question. So there are a couple of pretty obvious reasons, and I'm sure from my experience drinking beer and talking about this with people, you very quickly realize that there are many, many more applications, but I've listed out about 5 key ones here. The first of which is high availability. So you've got paying customers in the green box at the top there. You would ideally like them to be able to be serviced, you know, whether it's your ad serving system, your Google search, your Google Maps, your, you know, whatever application you're doing, you would like them to be served irrespective of whether a particular data center has a power failure today, whether the data lines into that data center have been disrupted in some way, earthquakes, typhoons, floods, etc. And the way we typically do that is by having some kind of a cross-cluster load balancer inserted between your clients out on the internet and the data centers. Within the data centers, could anyone grab me a glass of water or something? Within the data center, we have a separate kind of load balancing, and most of you have probably used the Kubernetes services abstraction that provides a degree of load balancing. But before you even get to a cluster, you need to decide which cluster to go to, and we'll talk a little bit more about that later. The thing that people typically think about in the context of high availability and tolerance of data center outages, thank you, sir, is these very dramatic, you know, acts of God kind of things. Hurricanes, typhoons, cloud providers who often come up with very dramatic sounding reasons for why a data center went down, earthquakes, lots of lightning in the news articles, etc. The reality is, in fact, these things do happen, obviously, and they, you can put numbers on them. They happen, in the sort of third and fourth nines area of your availability. What happens a lot more often is that someone reconfigures something with all the best intentions and screws it up completely, and the entire data center goes down. Is that, I'm seeing lots of nods in the audience. Has that ever happened to anybody? No, I didn't think so. And infrastructure upgrades. So, we've got this great new authorization system that we're just going to plug in the back. Shouldn't cause any problems. We'll just reconfigure something to talk to this new authorization system. Oh, we forgot to put all the users in the authorization system. Everything fails. Whole data center goes down. No earthquakes, no thunderstorms, nothing else. Just someone with a fat finger and a bad editor or something along those lines. Lots of interesting war stories to tell about that, but maybe I'll do that over beers later. What else can we talk about here? So yeah, and there are a couple of interesting variants here. Do we use multiple availability zones in a single cloud provider, which provides various benefits? If we're particularly nervous about a given cloud provider, and maybe that cloud provider in inverted commas is our local data center at our home office, our on-premise stuff, if that one fails, we might want to have something on a different cloud provider just to further reduce the chances of both of them failing at the same time. And I think both Google and Amazon have had more than one in the history of those companies, global outages where everything went down across all data centers. Typically doesn't happen for very long. Some very important people get phoned in the middle of the night when these things happen, and they tend to get fixed quite quickly, but they do exist and they have been in the news. There was one, Google had I think a 3 or 4 minute outage about 2 years ago perhaps, where the entire global network stopped sending traffic to our data centers, which was considered a bad thing. Fortunately fixed within a few short minutes. Whoops. Okay, so that's reason one why you might want to do multiple cluster deployments and why you might want to have something in between your clients and multiple Kubernetes clusters. Reason number two, application migration. I'm sure many of you have and are still probably wrestling with the idea of moving legacy and other applications from your on-premise data centers into various cloud environments, whether they're infrastructure as a service or containers or PaaS or anything else. It's often a not entirely seamless operation. And certainly being able to automate a lot of that and roll it back if things go wrong is highly beneficial. And it's another one of the possible benefits that you get from a cluster federation situation. What else can we talk about there? So yeah, I mean, it is totally true. You can do this stuff manually. You can go and spin up your application, Kubernetes or otherwise, in a different cloud provider or off-premise in the cloud, and you can test that it all works correctly, and you can hopefully then switch your customer traffic over and tear down the other stuff. But in the same way that you can do software upgrades the same way in Kubernetes, you don't really need our upgrade infrastructure to do that for you. You could do that all manually, but it's tedious, error-prone, tends not to work properly, and we've learned from lots of hard-won experience how to do it, reliably and be able to roll back when these things go wrong. And the same applies to migration between data centers and between cloud providers, for that matter. And of course, the last item on there. Some people asked this morning in the forum discussion, why did Google do Kubernetes in the first place, and why did we open source it and give it out to everybody? You guys crazy? Well, the last bullet point on the slide might give you some indication of one of the reasons, which is, if you can reduce the amount of friction that is incurred in moving from on-premise data centers into the cloud or from one cloud provider to another, Google believes that we have, pretty good data centers and pretty good networks and pretty good storage, etc. If it's easy for people to move in there, that turns into dollars at the end of the day as well. We even have an animation. Look at that. So we're doing an application migration from an on-premise cluster to an in-cloud cluster. Look at that. Excellent. There's quite a few more of those coming. I must warn you. I hope you don't get bored with that animation. Okay, reason number 3, policy enforcement. The previous talk, there was quite a lot of time spent on, how do you express policy, how do you enforce it, how do you audit that it has actually been enforced. Some of these things are kind of pretty boring to techie engineers, but a lot of this is what drives the business world out there, and the guys who write the big checks care a lot about these things. So we, by implication, need to care about them too. And some of the stuff can be pretty cool. So you can imagine policies around data storage, like if you have data that has certain properties or containers that have certain labels on them, these need to be in EU legislation compliant data centers. That might be a reasonable policy to specify as a company as a whole. And how do you now make sure that you're a big Fortune 500 company, you've got tens of thousands of engineers scattered all over the world, and some clever person decides this is our policy, but it's a different story to get 10,000 engineers to make sure that all their stuff is in the right data centers that have the right labels on them. So it becomes much easier to enforce that if you have an intermediate layer which can enforce these policies. So you don't even ask the engineers where they want their applications to run. They just tell the cluster federation system, go and run my application, and it decides whether this is an application that requires EU legal compliance and sits in the right data center. The same applies to different cloud providers. You might have different pricing plans available from different cloud providers. You might have long-term agreements with them. You might have overflow capacity requirements. It makes a lot of sense to automate the decision as to where to deploy, in which clusters to deploy applications on the basis of this kind of business logic. Again, from an engineering point of view, not always the most exciting sounding stuff, but it can do some pretty impressive stuff. And of course, having this all go through a central point of control gives you a very good place to audit things. So you can set authorization policies centrally. You can log exactly who's done what, which applications and which data has been put in which data centers. Makes it a much easier exercise. And bear in mind, even though on the right-hand side of that slide we only have, pictorially 3 data centers, this very quickly becomes, 30 data centers. 5, 10 on each continent, and keeping track of exactly what's running where and which ones have been through various different compliance checks, etc., is a non-trivial exercise. And we have another animation. We're moving from a US cloud cluster to an EU cloud cluster because we had some new data laws imposed upon us. Same animation as before for those very astute observers. The next, that's the one. The next one, of course, vendor lock-in avoidance. And I've got to be a little bit careful with my words here, but let's just say that if you put all your eggs in any one basket, and there are many of those baskets that we know about in the past of the IT industry, you tend to end up paying a much higher price for that basket if you can't get out of that basket. If, on the other hand, you have your eggs in 3 different baskets, every year you can go to the owners of those baskets and you can say, we do have 2 other options. We're actually running all our applications there already. Would you entertain a better price for us? It makes for a much more productive business discussion than, we have all our eggs in your basket. We would like you to charge us less for the basket, please, but we have no other baskets. You can imagine those discussions don't often end in happiness for the person on that end of the negotiation table. So that, yeah, I mean that's pretty straightforward. They're also, over and above those kind of sitting in a boardroom haggling about very large checks type of arguments. There are also reasons where one cloud provider might simply be better than another one for various reasons. Workload characteristics, one cloud provider might have great storage but bad networking, or vice versa. It's really useful to be able to shovel the stuff around automatically based on the properties of the workloads. And it's possible, and we've done this at Google, to analyze the properties of workloads and move them between different data centers which had, for example, you might have older generation hardware in one data center, newer in another one. Certain workloads work really well on the old hardware, other workloads like the new hardware, so you just move the stuff around automatically. Budget, some of the pricing of these things is different. Different workloads end up using different amounts of network, different amount of storage, so placing a given application in one cloud provider might be cheaper than another one, but a different application might be cheaper running in the other environment. And you can do that sort of analysis and migration automatically. Performance, availability requirements, similarly, different cloud providers, your on-premise data center might not be run as well as Google's, and in some cases that might be fine and it's cheaper, but in other cases if you need 5 nines of availability, you're probably better off going with somebody who does this stuff for a living. How are we doing for time? When did I start? Okay. We've done this one, and we have another migration animation. Look at that. Migrating from Google Cloud Platform to AWS. What? No, that seems to be the wrong way around. That's clearly, must have that one in reverse. Definitely going the wrong direction. Capacity overview, that's another one, of course. Most of you have probably read about this. Cloud bursting is the name that people give it. It's one of those things that kind of caught the imagination, particularly when multiple cloud providers, in fact, even from the early days when we sort of started with this Amazon Web Services and EC2 idea, one of the easy to understand applications of this was, well, our home data center is full, and Amazon had this problem themselves. 40% of all their sales happened in December and the 3 weeks before Christmas, and so they had this like 40% of the data center capacity sat around idle for 11.5 months of the year. And if you've looked at the margins that Amazon runs on, they don't actually have 40% margin to leave lying around in their data centers. And a lot of other companies have similar, even if they're slightly different problems, they don't really want to keep a 40% overhead in their data centers. They'd rather have the sort of ambient load run on-premise, and for those 3 weeks of the year before end of tax year or before Christmas or whatever it happens to be, then overflow into some other place like a cloud provider. And that makes, becomes much simpler if you have a central place like an Ubernetes cluster federation control plane, where you can make these decisions, decide where to overflow, when to overflow, move stuff back again when holes start opening up, for example, in your on-premise data center, assuming that that's your preferred place to run things. That's a pretty obvious choice, and you can make, again, intelligent decisions based on optimizing the utilization of independent data centers, the costs of the running things there. We had a discussion over lunch about often an on-premise data center is a sunk cost. It's paid for, essentially running stuff inside that data center is free, give or take. Whereas running stuff in a cloud provider can very quickly, and particularly if you have bugs in your software and poor quotering in place, you can very quickly rack up, $100,000 bills at Google or Amazon with that accidental endless loop that fired up 32 core machines for the month before you got your bill at the end. So yeah, and performance. On-premise data centers might be running bare metal applications. In some cases, your software could care about that. Things like network latency can make a big difference. Especially in the tail. You might want to run certain applications on your bare metal on-premise and the other stuff in a virtual machine environment at cloud providers. All right, so I'm hoping that everyone's on board so far. I'm sold. So where do I sign up? Well, there's a couple of challenges. As I'm sure you've guessed, I've glossed over some technical details. The first and obvious one is, these things are not all the same. So every one of your clusters is not equally far from every other one. And the connectivity between them is not always going to be identical. So, on the left-hand side, we have, let's say, Google Cloud. We have 2 availability zones in there. We have high-speed networking. We have various things that might operate between those 2 zones, but which don't apply to a different cloud provider. So we have a different kind of network connectivity. We have different ways of connecting our pods together, etc. So that provides challenges. Even within an individual cloud provider, and I tried to illustrate that down at the bottom there, 2 zones within a region. We have metros in the Google data center architecture. We have these metros, and we have multiple availability zones within a metro, and the bandwidth and the latency and network properties in general and the cost are very, very different within a metro than if they're, for example, transcontinental between different metros on different continents. So, you can't just wave your hands and make all that difference go away. You have to be able to deploy things intelligently so they still work. Service discovery is also a problem, or potential problem. Inside Kubernetes and between pods, we've got pretty civilized service discovery mechanisms, but those don't always work across clusters and between cloud providers, so we have to sort of fudge the gaps there. The dream world is we'd like to be able to take an application, and if it runs in one cluster, we'd like to be able to give it to Ubernetes and have it run across multiple clusters and everything to just work. Now, clearly there's some challenges to overcome. Also, once you've got large numbers of these clusters, it very quickly becomes obvious that monitoring and alerting and auditing, for that matter, become a fairly substantial challenge. How do you keep track of the state of 30 clusters? And how do you figure out what happened across 30 clusters if you want to audit a security breach, for example? Cross-cluster load balancing is another one, somewhat related to service discovery, but different. And there are various different approaches. We've got pretty sophisticated, well, I guess some would argue otherwise, but reasonably sophisticated load balancing in Kubernetes within a cluster. And many of you who've deployed such a thing will at least know something about how that works. But what we typically do, as I mentioned a little earlier, is we first have to get, particularly outside traffic coming from the internet at large, we need to get that to the correct data center before we can even start load balancing it across the machines and the nodes in the data center. So there are various approaches to that. The sort of relatively dumb one is just to use DNS to either send it to a random data center, which is generally not a good idea. You've got things like GeoDNS, which will automatically send a client to its closest data center. And there are geographical databases inside the DNS server that'll figure out this is your source IP, you must be in this country, therefore let me send you to a close data center rather than one across the other side of the world. We can also do more sophisticated things than that. So we can report out of a given application running in one data center what its load levels are. And if it's overloading, you don't want to send any more user traffic there. You'd rather send it to a data center perhaps a little further away that is less loaded, and the overall latency might be lower. So we can do that sort of thing with service monitoring and health monitoring. Similarly, if an application goes down in one data center, you don't want to send a whole bunch of traffic there. You want the DNS system to monitor that, to automatically detect that that particular endpoint in one data center entirely is down in much the same way that the Kubernetes service monitoring works, and shift the traffic away from that data center, typically via some form of DNS. And we have L7 load balancers available. I missed Brendan's talk this morning. I don't remember whether it made it into 1.1, but I think we have L7 load balancers available inside our data centers now for Kubernetes. I think we've spoken about everything on that slide. And that one. Location affinity, and that sort of gets back to some of the stuff we spoke about a couple of slides back. The networks are not all the same. So turns out that you have quite a few different classes of applications. We've got what I call strictly coupled applications, which do a lot of communication between the different pieces of the application. They've got high bandwidth requirements, low latency, high fidelity. They don't handle lossy lines very well. These ones cannot easily span clusters, and that policy can be enforced by the, I'm being given the Kelsey wave. I think that means that I'm starting to run out of time. Okay, but let me speed up a little bit here. So at a high level, strictly coupled, loosely coupled, and preferentially coupled. So loosely coupled are those applications that generally don't care about how close their pods are together, and one can fairly easily distribute these across multiple clusters. You can migrate entire applications from one cluster to the next incrementally, one pod at a time, and for the most part they don't care. Preferentially coupled, we ideally want them all to run in the same, all the components of an application to run in the same data center, but they can actually tolerate for limited periods of time being split between multiple data centers. For example, if we're migrating from one to another. And there's more stuff in the documentation that you can read about there. We also have negative affinity. Often we don't want to, for example, two replicas of data to be in the same zone, because if that zone goes down, we lose all the replicas. And there are all sorts of, interesting points along the continuum here. We don't want things on the same rack, or we do want them on the same rack. Racks tend to fail in concert, as most of you probably know. Same with zones. Zones typically correspond with, areas that fail. They have a single power supply or a single data feed. Metro regions are, we might have multiple zones in a metro region, but, if you have a huge flood or a wide-scale power outage, an entire metro region can go out. And then we have absolute location affinity. People want their applications to be close to their customers, and as we mentioned earlier, sometimes they have to be within certain or political jurisdictions. Monitoring, we want to be able to look at all this stuff in a coherent fashion. Who saw the demo this afternoon? I can't even remember the name of the company, but I was just completely blown away. What was that awesome monitoring? I was blown, that was just awesome. Every now and again you see something you think, that's what I want, So please do make that cluster federation aware. We didn't even get onto the implementation. The API is compatible with Kubernetes. Most of the state resides in the underlying Kubernetes clusters, so you get all sorts of benefits from that, better scalability, so the clusters scale independently of each other. The control plane, the Ubernetes control plane at the top right-hand corner of the slide there, scales with the number of clusters, not the number of nodes or the number of pods. This is all good. We get much better fault isolation. So if Ubernetes, for example, the control plane top right there fails catastrophically, your application still carries on running. All the replication controllers and services and load balancers and everything else in the bottom two clusters keep on going. Everything's happy. The design principles of the implementation are very similar to the existing Kubernetes stuff. You've heard lots about this stuff, control loops, driving desired state, or rather current state to desired state, etc. Modular, it's all good. This is probably the bit that I should finish off with, as it's probably what a lot of people are interested in. What is the current status and what are our plans from here? We recognize that building that full federation system that I described in the architecture diagrams early on in the talk is going to be a non-trivial exercise. And yet there are quite a few customers who are very, very, very keen to get to a very basic situation where they can run an application across multiple availability zones and have it not fail if one of them fails. So that milestone we've tagged as Federation Lite. And that's a single logical Kubernetes cluster, but running across multiple independently failing availability zones. We actually have, is Justin in the audience? Where is he? Ah, there he is. If you want it out sooner, speak to Justin. He's sitting on the back corner there. But we have a prototype of that working in AWS at the moment. There's some minor sort of differences between AWS and GCE that are being ironed out. But that should be available for sort of tire kicking purposes in the next month, Justin, and hopefully productionized early next year. The federation proper, with a full independent control plane and federating arbitrary numbers of clusters across different cloud providers, we hope to have in a sort of kick the tires state in Q1 next year. It's certainly not going to do all the whiz-bang things that I just spoke to you about in the first iteration, but it'll provide the basis for much of what I've spoken about. And we hope to have that productionized not too long after that. And then GKE you can expect to have hosted Federation Lite, Ubernetes Lite functionality. Don't want to sell any of the GKE operating guys down the river here, but sort of Q1, Q2 next year. And then there are many other third-party applications that are already working with us on the Ubernetes design and implementation, and who are porting some of their existing automation infrastructure that sits on top of Kubernetes to run on top of Ubernetes. If you want any more, there's a fairly detailed documentation on most of what I've described here, going into a lot more detail. There's a special interest group that you can join. There's a mailing list, etc., where discussions are happening. There's a working group that meets every 2 weeks. The notes from that working group are at that URL. And last but not least, my contact details are at the bottom. So if you need to ask any questions, or better still, want to volunteer to write lots of code, get hold of me. Done.
Awesome. Thank you, Quinton. So that's the end of KubeCon Day 1. There's a welcome party upstairs in about 4 minutes at 5 o'clock. And we're going to end the day with our chant. So you will rise. So I don't have to give out instructions this time. How many people know what hip-hop is? Be careful with your YouTube searches. If you just type that in YouTube, it might get dangerous for you. So be careful. When I say Kube, you say Kube. Louder this time. When I say Kube, you say Kube. Kube.